In this video, I will introduce the work of visually explaining video understanding networks with perturbation methods. Deep neural networks have achieved considerable progress in many video understanding tasks in recent years. However, in most cases, although the prediction results by these networks are competitive, most of them are working like black boxes, and it is unclear for us why a result is predicted for one input. So as one way to explain this black box video understanding network's prediction, we can try to find in the input which pixels or regions are taken important by the network. We call the method for this task as the visual explanation method, and they can produce results like this. The challenge for visually explaining video understanding networks comes from 2 points. First, there are many different network structures. And secondly, compared with an individual image, video possesses an additional temporal dimension, and spatio-temporal dependencies exist between frames. However, previous works for visual explanation show limited abilities in resolving the challenges because they come short of 3 points. First, some of them rely on the modified backpropagation rules, which are often inconvenient to implement. Some methods work only for a specified network structure and are hard to be generalized for the diversified structures. Partial methods can only generate results with the reduced resolution in both temporal and spatial dimensions. As a result, one easy-to-use method that is generic for diversified structures is still absent. In this paper, we propose a visual explanation method for video understanding networks. We call the method STEP. It is a model-agnostic perturbation-based method enhanced by a novel regularization item for spatio-temporal smoothness. The method tries to find a subset of the input which is as small as possible while retaining the prediction accuracy on a specified target label. Since it generates results only via iteratively perturbing on the video and observing the corresponding output, it can work for any networks without knowing the internal architecture. Also, the proposed regularization item enhances the method to achieve competitive results by employing spatio-temporal dependencies between frames. In specific, the key insight of the regularization item for spatio-temporal smoothness is to constrain the continuity and shape of the preservation in each small spatio-temporal region. Taking to the video is the action label of fencing as an example. If we directly perturb on the video without taking into account the smoothness in temporal, the results will come to this. We can find that the coherence of the preserved regions in each frame is hardly ensured, and the output probability cannot be retained by the fragmented preservations. Actually, discriminative information in video commonly continues for a period of time and changes in irregular shapes. This makes it hard to realize the shape regularization directly for the preserved regions. To overcome the challenge, instead of regularizing the shape in a whole, we decompose the preserved regions into small elements with a fixed shape and then ensure the smoothness in each small local neighborhood. The result after using the regularization item comes to this. We can see it is coherent, but also the accuracy prediction are also retained. For the experiment, it can be seen that on two data sets and two models, our method STEP can well locate the key regions and give different but consistent masks for different frames. Here we show more visualization results of STEP in the video form. Qualitative experiments also demonstrate superior results compared to the baseline methods. Thank you very much for your attention. For more information, please read our paper or project code linked here.